Hello guys, and welcome back to this new video about the GCP Essential Cloud Infrastructure. We'll have a look at the foundation in this playlist. Um, so let's go. Let's get back from where we left yesterday. So this is the Essential Cloud Infrastructure course in Cloud Skill Boost. Resume the course. This course is
In this
about
module, we will
well, how to interact with Google Cloud, virtual networks, virtual machines, and yeah, there are a lot of labs about these resources. Today we'll start with the virtual networks. I'm not sure if we'll finish everything today as it's a long module, this one. I will say that the first goal will be to do the first lab, and then we'll see. So let's go.
In this module, we will be covering virtual networks. GCP uses a software-defined network that is built on a global fiber infrastructure. This infrastructure makes GCP one of the world's largest and fastest networks. Thinking about resources as services instead of as hardware will help you understand the options that are available and their behavior. In this module, we start by introducing Virtual Private Cloud, or VPC, which is Google's managed networking functionality for your cloud platform resources. Then, we dissect networking into its fundamental components, which are projects, networks, networks, IP addresses, routes, and firewall rules, along with network pricing. Next, you will explore Google Cloud's network structure in the lab by creating networks of many different varieties and exploring the network relationships between them. After that, we will look at common network designs. This map represents Google Cloud. On a high level, Google Cloud consists of regions, which are the icons in blue, points of presence or POPs, which are the dots in blue, a global private network, which is represented by the blue lines, and services. A region is a specific geographical location where you can run your resources. This map shows several regions that are currently operating, as well as future regions. Regions indicated with blue icons have 3 zones. Iowa is an exception, where the region called US Central 1 has 4 zones: US Central 1A, US Central 1B, US Central 1C, and US Central 1F. For up-to-date information on regions and zones, please refer to the documentation in the slides. The POPs are where Google's network is connected to the rest of the internet. Google Cloud can bring its traffic closer to its peers because it operates an extensive global network of interconnection points. This reduces costs and provides users with a better experience. The network connects regions and POPs and is composed of a global network of fiber optic cables with several submarine cable investments. Let's start by talking about GCP's network interconnection points.
I'm interested in this map. So they have this point of presence in Sydney, Melbourne, and Perth, maybe. Then something in Jakarta and Singapore, Mumbai and Delhi, Hong Kong, Taiwan, Osaka, Tokyo, and Seoul, then Doha. Johannesburg. Okay. So they coincide with the Occidental friends map. Okay. This should be Medellin or something like that. Sao Paulo, Santiago, and maybe Buenos Aires.
This reduces costs and provides users with a better experience. The network, we're talking about GCP's network and specifically Virtual Private Cloud, or VPC.
So let's start with these networks.
With GCP, you can provision your GCP resources, connect them to each other, and isolate them from each other in a virtual private cloud. You can also define fine-grained networking policies within GCP and between GCP and on-premises or other public clouds. Essentially, VPC is a comprehensive set of Google-managed networking objects, which we will explore in detail throughout this module. Let me give you a high-level overview of these objects. Projects are going to encompass every single service that you use.
Nice. So VPC is a comprehensive set of Google-managed networking objects. Great.
Including networks. Networks come in 3 different flavors: default, auto mode, and custom mode. Subnetworks allow you to divide or segregate your environment. Regions and zones represents Google's data centers, and they provide continuous data protection and
Regions and zones represent Google data centers, and they provide
high availability. VPC provides IP addresses for internal and external use, along with granular IP address range selections. As for virtual machines, in this module, we will focus on configuring VM instances from a networking perspective. We'll also go over routes and firewall rules.
Let's go.
Let's start exploring the VPC objects by looking at projects, networks, and subnetworks.
Projects are the key organizer of infrastructure resources in Google Cloud. A project associates objects and services with billing. Now, it's unique that projects actually contain entire networks. The default quota for each project is 15 networks, but you can simply request additional quota using the Google.
They're talking fast.
Projects, networks, and subnetworks.
Projects are the key organizer of infrastructure resources in Google Cloud. A project associates objects and services with billing. Now, it's unique that projects actually contain entire networks.
A project associates objects and services with billing. Now, it's unique that projects actually contain entire networks. What the fuck does mean this phrase? Now, it's unique that projects actually contain entire networks. The default quota for each project is 15 networks, but you can simply request additional quota using Google Cloud Console. These networks can be shared with other projects, or they can be paired with networks in other projects, both of which we will cover later in Architecting with Google Cloud Compute Engine course series. These networks do not have IP ranges, but are simply a construct of all of the individual IP addresses and services within that network. Google Cloud's networks are global, spanning all available regions across the world that I showed earlier. So you can have one network that literally exists anywhere in the world, all simultaneously. Inside the network, you can segregate your resources with regional subnetworks. I just mentioned that there are different types of networks. Let's explore this type of networks in more detail.
Every project is provided with a default EXC network with priest subnets and firewall rules. Specifically,
what the fuck? Why so bad this audio? So a default VPC network with preset subnets and firewall rules. Specifically, a subnet is allocated for each region with non-overlapping CIDR blocks and firewall rules that allow ingress traffic for ICMP, RDP, and SSH traffic from anywhere. As well as ingress traffic from within the default network for all protocols and ports. So from outside, we can, by default, we can contact from outside through ICMP, RDP, and SSH, from inside with all the protocols. The automatically created subnets use a set of predefined IP ranges with 20 masks that can be expanded to 16. All of these subnets fit within the CIDR block. Okay. This is an internal type class A, if I'm not wrong. Okay, so class A, private IP range, public IP range. Okay. Class B is the classical one used in private LANs. No, this of this 172? The classical one is the class C. In class D IP address range to host and used for multicasting. Okay. For general use. Okay. So this is class A. Therefore, as new Google Cloud regions become available, new subnets in those regions are automatically added to auto-mode networks using an IP range from that block. A custom mode network does not automatically create subnets. This type of network provides you with complete control over its subnet and IP ranges. You decide which subnets to create and which regions you choose, and using IP ranges you specify. These IP ranges cannot overlap between subnets of the same network. Now you can convert an auto mode network to a custom mode network to take advantage of the control that custom mode networks provide. However, this conversion is one way, meaning that custom mode networks cannot be changed to auto mode networks. So carefully review the considerations for auto mode networks to help you decide which type of network meets your needs. Google Cloud now supports IPv6 in a custom VPC network mode. For example, you can configure IPv6 addressing on dual stack VM instances running both IPv4 and IPv6. You can learn a lot more about IPv6 in the networking Google Cloud.
You can learn a lot more about IPv6 in the networking in Google Cloud course.
On this slide, we have an example of a project that contains 5 networks. All of these networks span...
Okay, let's see this. The audio sounds good. So we have public internet, the segmentation for region, and the segmentation for network by network, all in one project. We have instances A and B in regions US 1, US East 1, and Europe West 1. They're communicating over internal IP, even they're in different regions. This is because they're in the same network. And then we have C and D communicating over the public internet, over external IPs. Even they are in the same region because they are in different networks. So it's cool. Okay, nice schema.
Span multiple regions across the world, as you can see on the right. Each network contains separate virtual machines, A, B, C, and D. Because VMs A and B are in the same network, network 1, they can communicate using their internal IP addresses, even though they're in different regions. Essentially, your virtual machines, even if they exist in different locations across the world, can take advantage of Google's global fiber network. VMs C and D, however, are not in the same network. Therefore, by default, these VMs must communicate using their external IP addresses, even though they're in the same region. The traffic between VMs C and D isn't actually touching the public internet, but it is going through the Google Edge routers. This has different billing and security ramifications that we'll explore later. Because VM instances within a VPC network can communicate privately on a global scale, a single VPN can securely connect your on-premise network to your Google Cloud network, as shown in this.
So on-premise, Google VPC is global. Therefore, in the same Google Cloud VPC, we have 2 machines which can communicate internally. Then we have a VPN gateway, which allows my own premises to communicate with all the VPC resources, so with both the VMs.
Diagram. Even though the 2 VM instances are in separate regions, US West 1 and US East 1, they are leveraging Google's private network to communicate between each other and an on-premise network through a VPN gateway. This reduces cost and network management complexity. I mentioned that subnetworks work on a regional scale. Because a region contains several zones, subnetworks can cross zones. This slide has a region, region 1, with 2 zones, zone A and zone B. Subnetworks can extend across these zones within the same region, such as subnet 1. The subnet is simply an IP address range, and you can use IP addresses within that range. Notice that the first and second addresses in the range, .0 and .1, are reserved for the network and the subnet's gateway, respectively. This makes the first and second available addresses, .2 and .3, which are assigned to the VM instances. Other reserved addresses in every subnet are the second to last address in the range and the last address, which are reserved as the broadcast address. To summarize, every subnet has 4 reserved IP addresses in its primary IP range. Now, even though the 2 virtual machines in this example are in different zones, they still communicate to each other using the same subnet IP address. This means that a single firewall rule can be applied to both VMs even though they're in different zones.
Okay, a firewall rule, for example, is allow communication from outside over SSH. So this will be applied to all the region VMs. Okay, then we have zones, and each VM can be part of a different zone, being part of the same subnet, even if in different zones.
Speaking of IP addresses of a subnet, Google Cloud VPCs let you increase the IP address space of any subnet without any workload shutdown or downtime. This diagram illustrates a network with subnets that have different subnet masks, allowing for more instances in some subnets than others. This gives you the flexibility and growth options that meet your needs, but there are some things.
Okay, so 24 will mean less machines possible, range of 16 more machines. So in region A subnet, this is a subnet which goes crossing maybe different zones, but the point is that the subnet is bigger because it's a bigger range. Therefore, more VMs can be attached to that subnet.
Things to remember. The new subnet mask must not overlap with other subnets in the same VPC network.
Cannot overlap with other subnets.
But there are some things to remember. The new subnet mask must not overlap with other subnets in the same VPC network in any region. Each IP range for all subnets in a VPC network must be a unique, valid CIDR block. Also, the new subnet IP ranges are regional internal IP addresses and have to fall within valid IP ranges.
New subnet IP ranges have to fall within valid IP ranges.
Subnet ranges cannot match, be narrower, or be broader than a restricted range. Subnet ranges cannot span a valid RFC range and a privately used public IP address range. Subnet ranges cannot span multiple RFC ranges. The new network range must be larger than the original, which means the prefix length value must be a smaller number. In other words, you cannot undo an expansion. Now, auto mode subnets start with a /20 IP range. They can be expanded to a /16 IP range, but no larger. Alternatively, you can convert the auto mode subnetwork to a custom mode subnetwork to increase the IP range further. Also, avoid creating large subnets. Overly large subnets are more likely to cause CID or range collisions when using multiple network interfaces and VPC network peering, or when configuring a VPN or other connections to an on-premises network. Therefore, do not scale your subnet beyond what you actually need.
Okay.
Let me show you how to expand a custom subnet within GCP. I've already created a custom subnet with a /29 mask. A /29 mask provides you with 8 addresses, but of those, 4 are reserved by GCP, which leaves you with another 4. Let me show you how to expand a custom subnet within GCP. I've already created a custom subnet with a /29 mask. A /29 mask provides you with 8 addresses, but of those, 4 are reserved by GCP, which leaves you with another 4 for your VM instances. Let's try to create another VM instance in this subnet. So here we are on the GCP console, and I have my 4 instances. And if I go into the network interface details here, you can see that these are part of a network, and I have a subnet here. And if I drill further into that, you can see that I currently have a /29. So let's go back and try to create that other instance. I'm just going to click on Create Instance. I don't need a very large machine. I'm OK with a micro. And let's hit Create. And ideally, we should be getting an error now about the fact that the IP space should have been exhausted. So we're just going to wait for that. You can also follow this along in the notification pane up here. You can see that it is trying to create that right now. And so we're going to wait for that and see if we get an error here in a second. And once we have that, we're going to go ahead and expand the subnet. So here we can see that the instance creation has failed. I can hover over this, and it's just telling me that the IP space of that subnet has been exhausted, just as expected. And we actually have a retry button here as well as a notification pane. We're going to try to use that in a second once we expand the subnet to recreate that instance. Now, what's important is to note that all of these 4 instances are currently running, so we're not going to take any of these down during the subnet expansion. Now, to expand the subnet, I could go to VPC Network through the navigation menu, or I can go back by clicking on NIC0 here directly through the network interface details to the subnet. This is what I want to change, so let me click the Edit button. And let's expand this all the way to a /23. And this is going to allow a lot of instances, actually over 500 instances. And we're going to wait for this to update. And then we're going to head back and try to recreate that instance. So we can also follow this process along right here. It's still saving, so we're just going to hang on tight here. This should just take a couple seconds.
Okay.
All right, there we see it's complete. And now I still have that retry button here to recreate that instance. So let me actually click that. And I can head back to Compute Engine to see if that is going to succeed. So here we are, instance 5. It's being staged and will soon begin running. And let's see if this works out. We can see that it already has now an internal IP address allocated now that we've expanded the subnet itself. And if I refresh this, we can see that the instance is now created. That's how easy it is to expand a subnet in GCP without any workload shutdown or downtime.
Nice. Okay, so now
Now that we've covered
I need to repeat a bit the IP subnet mask scheme. Let's see if there's something graphical. Let's see this one. Okay. Maybe a YouTube video. Hey, network check. This guy is great. Maybe I will watch a video of his.
And that's how you use CRMs. Questions?
Or you can the subnet mask. This is how we create the networks of the world. This is where
This guy is great. I love him.
the magic of subnetting actually happens. That's why every IP address, even your IP address, has a subnet mask, and it tells us all the secrets about the network. Well, most of them. Some of them. You'll see. Here is my toilet and his IP address. Oh, whoops, forgot to flush. And here is his subnet mask. Now you may recall that Mr. Subnet Mask's job is to tell us how big our network is, how many IP addresses are there, and more. And you may even remember our little hack. Remember here? If we see a 255 in the subnet mask, we know that the corresponding octet, or the corresponding number in our IP address, is frozen. Just, it's done. It can't move, it won't change. But the big question is, why? Like, why does 255 mean that number stays the same? What's actually happening here? What's the subnet mask doing? Why is it 255? In this episode, we're gonna pop the hood on that. We're gonna see what the heck is happening. Why is it doing what it does? And why is the subnet mask so important? Now, in the previous episode, I gave you superpowers. You are now able to decode matrix computer code. I think, yeah, you can look at an IP address and convert it into binary, the language of computers, and you can convert it back. And actually, real quick, pause the video and see if you can convert our current IP address, the IP address of my toilet, into binary. Keeping in mind, this will be a lot easier if you use the help of our handy dandy chart and Nosferatu. So pause the video and go. Hey, time for a coffee break. And this coffee
So he says to convert IP address to binary. It was 92.68.32.5. Okay, so we have 1, 2, 3, 4, so 8 bit for each part of this IP.
toilet, home office, and then Antarctica. Or you may have this old server that you have to make sure Okta and then to companies, making them lose. Sponsored by Big. Oh, that's good. Now, while you're sipping that coffee, let's talk about something a bit scary: cyber breaches on the dark web, and ultimately they lose. Here's the reality: managing. Actually, it's kind of almost impossible. Hundreds, sometimes thousands, tens of thousands of endpoints that you have to make sure stay safe. From home, coffee shops, and the cloud, and all laptop to a phone to a kiosk, sitting underneath someone's desk in like Kansas or something. How are you going to find and update that when you don't even know it's there? It wasn't going to be an easy coffee break. So how do companies, small like HCLs, big, see all, I mean stinking all, whether it's on-prem in your data center, at set, it could be sitting in someone's pocket, it could be, the phone or something, or the old grandpa's. Is there something I don't know about? Am I missing something? Did I update that server? A new vulnerability comes out and it's like the server patch. What OS does this run? Right? These amazing It's just a pain, right?
Man,
But
these
Big
guys
Fix will free up that time, so you can focus on the fun stuff. You've got your arm for these compliance standards saying, hey, yeah, everything's up to date, or hey, we know the system isn't patched, we're gonna patch it real quick. Really easy just to deploy fixes to things. And because it'll automate a lot of the tasks, it's just a pain, right? But Big Fix will free up that time, so you can focus on the fun stuff, the fun projects, things that challenge you, and check out Big Fix. I got a link below, bigfix.com. You can actually sign up for some free training to see, hey, what can this do for me? It can do a whole lot. And hey, thanks for having some coffee with me. Let's get back to the video. Unpause, coffee break. And done. This is my toilet's IP address and binary in computer code and matrix code. And if you're wondering, how did he do that? Go back and watch the previous episode. I show you how it's remarkably simple and kind of fun. Actually, no, it's very fun. Just go do it. Now, what we did not do in the last video is convert our subnet mask into binary, which is something we totally can do, should do, and will do right now. And this one's kind of remarkably easy. So for example, if I'd bring my first number down here, my first octet, 255, and I want to see if the first bit is going to be on or off, 1 or 0. Can 128 be subtracted from 255? Yes, 100%, yes it can. That first bit is on. So 255 minus 128 gives us 127. Bring that over here. Can we take 64 away from 127? Yes, we can. That sweet spoiler alert digit numbers 28 plus 64. Every bit in that octet will be on 55. Knowing that 255 means every bit in that octet will be on, go ahead and finish out the mask. It's kind of easy, right? This is our subnet mask converted into binary. All ones all the way across in the first 3 octets. The last one, also easy because 0 and binary is still 0. All the bits are off because you can't take any of these numbers away from 0. Now here is where it's all gonna come together and make sense. And why we're converting stuff into binary anyway. Like, what's the point? Here's the point. Because if you listen closely, these 1s and 0s in our subnet mask, they're speaking to us. They're telling us something. They're whispering things about our network, dark mysteries. If you can't hear, I'll go ahead and tell you. Sorry, that was stupid. But stick with me, take a sip of coffee. Get excited. When you're looking at the subnet mask, the 1s tell us, they whisper to us which part of the IP address are the network bits. So looking here, we can tell that, dude, we got lots of 1s all the way down in our first 3 octets, which means every one of these bits up here in our subnet mask, all the way down through all 3 octets, are the network bits. So network bits, aka the part of the IP address that won't change and tells us which network we're on. And then it's also whispering something else to us here. Listen closely, listen. The 0s, they tell us which parts of the IP address are host bits. So looking at our mask, we can see that the entire 4th octet is all 0s. So we know in the IP address, every bit in the 4th octet will be a host bit, meaning each of these bits can be used to create an IP address in that network and be assigned to that host. Now I know, this is weird, but here's one example of how this is cool. So the 0s tell us which bits are host bits, which also tells us how many possible hosts there are in the network. All we gotta do is count the number of bits. So looking here at our subnet mask, how many bits are 0s? I mean, they're all in the last octet. They're 8 zeros. And I know you're probably thinking, well, Chuck, I counted 8 zeros, but I know, looking at this network can have more than 8 IP addresses, and you're right. We're not done yet, because there is a formula with this. To see how many hosts can be in any network, here it is. This is so powerful, just put this in your pocket, man. It's gonna be 2 to the power of zeros. How many zeros there are. So, for example, our example here. Let's grab a calculator. If I take 2 and I do my little power 2 of something, the caret, right? 2 to the power of how many zeros? 8. That gives us 256, which is absolutely correct. In this network, we can have 256 IP addresses. Now, of course, we can't use all of them. We have to subtract 2 to account for the subnet ID, or the subnet address and the broadcast address, the first and last IP address in the network, which gives us a total of 254 usable IP addresses. So the official formula would be 2 to the power of number zeros minus 2, because every network will have those 2 IP addresses reserved. So what this unlocks is something crazy powerful, because we know if we count the zeros, it gives us 254 usable IP addresses. But if we're like, hey, I need more than that in my network. I need like 500 IP addresses in my network. How do I get more? The simple answer is we need more zeros. We need more host bits to have more hosts. And to do that, we're gonna borrow, or we're gonna steal from the network. We're kind of like peeking behind the curtain of the next video, where we're really gonna break it down. I just wanna give you a peek. I can't tell you too much. But if I come over to this subnet mask here, I'm going to take away one of the network's bits. I want to take this last one and convert it to a 0. You're on the host team. Welcome. So now with that extra 0, how many hosts can this network have? Let's try it out. Let's use our formula. 2 to the power of number of zeros. Well, now we have not 8 zeros, but 9 zeros. So with our handy dandy calculator, 2 to the power of 9 will give us 512 addresses, which minus 2 gives us 510 usable addresses. So right here, I want you to understand what just happened. We converted our subnet mask and our IP address into binary. Before this moment, that was just like a thing you had to learn to do, an exercise. Now it's coming together, because what we just did is we went from having 254 available hosts, and we said, no, not good enough for me. I want more IP addresses in my network. Another one. I want more. I want 500. So we stole a bit from the network side, giving us more host. That's subnetting. You just subnetted. Because all really subnetting is changing the subnet mask to suit our needs. So here's a challenge for you real quick. We changed our subnet mask, which means the value in decimal is going to be different. It will no longer be 255.255.2550 because we changed something. We changed the third octet. So real quick, let's convert it back to decimal, back to the regular version of it, and see what it looks like. Now right off the bat, we know that the first 2 octets will be the exact first bam, B. And you may have been able to do this in your head. Possible IP addresses or 510 usable IP addresses. Now what just happened here was nothing short of magic, and I'm leaving a lot of questions unanswered. Like, hey, dude, what's our range of IP addresses? Like what's the network look like from like what IP address to what IP address? I'm not gonna cover that right now. We're gonna cover that in the next episode, where we're gonna break down subnetting even more and do a lot more of it. That's what I'm trying to say. But one more thing before we end this episode. I want you to notice in our subnet mask, the numbers are contiguous, which is a weird word I always love saying because it feels like continuous without adding a G, contiguous. Meaning that the ones will always be in a row. Like you won't suddenly have 1, 1, 1, 1, 0. No, that will never happen. The numbers are contiguous. It'll always be a row of ones and always be a row of zeros. So in this episode, we uncovered a few of the deep, dark secrets of the subnet mask. He tells us how big our network is. He tells us how many IP addresses we have. But in this episode, we actually dove deeper into how that works and what's actually happening. And in the next episode, we're gonna dive even deeper. Because these ones and zeros, they're not done whispering to us. They have some more secrets that we haven't uncovered yet. So I'll see you then. And by the way, if you want some extra practice converting your subnet masks into decimal and back to binary, virtual machines are amazing.
Let me search for subnetting. Oh.
So what is ClickUp? ClickUp is an all-in-one productivity software.
This one. So this was episode 5.
This is your home network. You have this subnet mask and this many addresses to use. But that's insecure. What are you doing? You can't keep all your stuff on the same network. So let's change that. But not in the normal way. We're gonna do something weird. Instead of simply adding networks like a lazy loser, I'm just kidding by the way, we're going to use the power of subnetting to break up your current network into 4 smaller networks: wireless, IoT, DMZ, and user. Now, why do it like this? Why use subnetting? Well, because you suck at subnetting. And in this video, we're going to change that. So welcome to episode 6 of You Suck at Subnetting, which does imply there are episodes 1 through 5. If you haven't seen those, go watch them. You'll need that knowledge to do the stuff we're doing here. So, armed with that knowledge and a delicious cup of coffee, networkchuck.coffee. Let's break up your current network into 4 networks using the power of subnetting. Now, before we dive in, can I tell you something? You don't just suck at subnetting, you suck at a lot of things. But that's okay, because we have IT Pro TV, the sponsor of this video. Fill in the blank, you suck at
most things.
Now you may recall from episode 5 that the subnet mask here, he tells us everything we need to know about the network. He whispers things to us. But to unlock his secrets, we'll have to convert him to binary using our good old buddy, Nosferatu. So Nosferatu, bring in our magic chart. And with a bit of flickering lights and skills you would have learned from previous episodes, this is what our subnet mask looks like in binary. A language that computers just about our network. For example, the 1s are our network bits, telling us about the network, and the 0s are our host bits, telling us how many hosts can be on this network. Now here is our mission. We have to manipulate this subnet mask. We need to change it and break it, and we need 4. We need to hack the host bits. We gotta flip them. We gotta bring him over to the dark side of the network bits. I don't know why the network bits are the dark side. I just felt like I should say it. Felt good. So cement that into your brain real quick. When you need more networks, you need more bits. And the only way you can get more bits is by hacking them or stealing them from the host bits. But how many of the host bits do we need to create 4 networks? That's where a new friend comes in, because I bet you didn't know that Nosferatu, he has a brother. Now, where Nosferatu helps us with decimal to binary conversion, his brother, Nosferatu, helps us with this problem. And he even has his own chart. Check this out. This is the Nosferatu chart. Because notice every single number in that chart is just the number in Nosferatu's chart times 2. So we say, hey, Nosferatu, we need 4 networks. And he says, okay, let me see here. Here's 4, and that took us 2 bits to get there. And that's exactly how many bits, how many host bits we have to hack and steal to create 4 networks out of our existing network. Now, just to hit this home a little bit, what if I asked you, hey, I need you to make 17 networks out of our existing network? Well, you would tell Nosferatu, hey, I need 17. So Nosferatu will look at his chart and go, all right, 16, that's not quite enough, we need 17. So I gotta jump to the next one, 32. And how many bits did we need to make 32? 1, 2, 3, 4, 5. So in that scenario, to have at least 17 networks, we would need to use 5 bits. We have to steal 5 bits from the host. But in our example, all we need is 4, which only required 2 bits. Thank you, Nosferatu. And now that we know how many we need to hack, let's go ahead and hack them. Let's flip them, bring them over to the dark side. So, starting at the beginning of our host bits, we'll hack 2 bits. Hacked, and we'll flip them over to the dark side. Gotcha, host bits. Now that right there is our new subnet mask. You just subnetted a network from 1 network into 4 networks. Now we're not quite done yet. Our mask is still in binary. Let's use Nosferatu, the first one, to convert our mask back into decimal. We know that all 1s are 255 because all bits are on. And in our 4th octet, we can see that the first 2 bits are on and the rest are off. And if we add 128 to 64, what do we get? 192. That's our new mask. And if we were to write that in CIDR notation, which is simply just counting all the network bits in our mask, we get 8, 16, 24, 25, 26. We have a /26 network. How cool is that? And there it is, our first network, new and shiny, so cool. But hold up, how many hosts are in this network? Like we can see the first IP address in the network is this, but where does it end? What's the broadcast address? How do we find that? How do we find the resulting networks and what their ranges are? We need to find the increment, which is super easy, by the way. Now, watch how hard this is. I'm totally kidding, watch this. The increment is simply the last network bit we have. So looking at our binary here.
I'm watching all of these, not because I would like to calculate them manually, but to understand.
In our subnet mask, there it is. That's our increment. And if we were to draw our last octet on our chart here, our increment is right here, and there it is in decimal. 64 is our increment. 64 is what we'll use to determine the size of our networks and what the ranges are. Let's go ahead and do it right now. Let's start with our first network. Of course, obviously. 192.168.1.0 through 192.168.1. This might trip you up a little bit. 63. Not 64 because remember, we're including the 0. The 0 is still an address. That right there is our first range, our first network. Let's do the next one. It'll pick up right where the last one leaves off. 192.168.1.64 through, and if you add 64 to 64, what do you get? 128. But remember, we have to include 64, so the number will actually be 127. And I think you got it. I'll fill out the rest real quick. Actually, pause the video. Your networks that we created out of 1 network using the power of subnetting. Each of these networks will have a subnet mask of 255, 255, 255.192. or /26. And a quick quiz to test your knowledge. How many hosts are in each of these networks? Keeping in mind that we now have less host bits, right? We borrowed some, we hacked some, we stole them. So now there's less hosts available in each network. Now, if you look at our increment, it's probably painfully obvious, right? But the formula from our past video still works. If you recall, to figure out how many hosts are available in any given network, we can look at our subnet mask in binary and count the number of host bits. How many are there? 1, 2, 3, 4, 5, 6. There are 6 host bits in this network, and the formula will be 2 to the power of host bits, which is 6, which we could use a calculator to figure that out. 2 to the power of 6, which is our increment, or we could simply ask Nosferatu, looking at our 6-bit, 1, 2, 3, 4, 5, 6. And then of course, if we account for the subnet address and the broadcast address, subtracting 2, we get 62 usable addresses in our network. So when someone says, hey, I need you to take this network and break it up into a million pieces, like maybe 6 or 7 or 12. you can take these 4 steps and do it. Like, it's awesome. In fact,
Calculate how many host beats you need to hack. Hack the host beats, find the increment.
I want you to do it right now. Here's your homework. Instead of 4, I want you to do 5 networks. Take that same network in this video and convert it into 5. I want you to paste the answer below. The subnet mask, I want to see the regular version and CIDR notation, and I want to see the ranges. Let's see what you got. Now I have good news. No matter what type of network you encounter, these 4 steps will work. If someone gives you a network requirement, we need this many networks, you can figure it out. But I will say this, we've been doing a Class C address, 192.168. It might feel a little weird when you do a Class B or a Class A address. Now, it will be the same. It just might feel weird. So if you want some extra practice with the other classes of addresses, I've got a link below. We got some extra training on this and some extra practice. But I do want you to take a moment and just think like, okay, here we are at episode 6 in our You Suck at Subnetting series. And you now have just learned how to subnet a network, to take a network and make it into many networks. And that's a pretty stinking big deal. You've come a long way, and this is a skill you will use in every area of IT. But we're not quite done. There are more things we're going to learn with subnetting, so keep an eye out, keep a lookout for the next few episodes. And again, a massive shout out to the sponsor of this video, IT Pro TV, who, unlike me,
Okay. Therefore, now we have an idea of what's going on with the subnetting in general and CIDR notation.
Google Cloud networks at a high level, let's go deeper by exploring the IP addresses. In Google Cloud, each virtual machine can have 2 IP addresses assigned. One of them is
So now that we've covered Google Cloud networks at high level, let's go deeper by exploring the IP addresses.
an internal IP address, which is going to be assigned via DHCP internally. Every VM that starts up and any service that depends on virtual machines gets an internal IP address. An example of such services are App Engine and Google Kubernetes Engine, which are explored in other courses. When you create a VM in Google Cloud, its symbolic name is registered with an internal DNS service that translates the name to an internal IP address. The DNS is scoped to the network, so it can translate web URLs and VM names of hosts in the same network. But it can't translate host names from VMs in a different network. The other IP address is the external IP address, but this one's optional. You can assign an external IP address if your device or machine is externally facing. That external IP address can be assigned from a pool, making it ephemeral, or it can be assigned from a reserved external IP address, making it static. If you reserve a static external IP address and do not assign it to a resource, such as a VM instance or a forwarding rule, you are charged at a higher rate than for static and ephemeral external IP addresses that are in use. You can use your own publicly routable IP address prefixes as Google Cloud external IP addresses and advertise them on the internet. In order to be eligible, you must own and bring a /24 block or larger.
Okay, so this is...
I just mentioned that VMs...
So until now we see what are the characteristics, the macro characteristics of the networks and subnetworks, how we can expand them, and how the IP addresses, what is the logic of the IP addresses assignation.
can have internal and external IP addresses. Let's explore this in the GCP console. So here I am on the Compute Engine page, and what I'm going to do is just create a VM and walk through the process of choosing your internal and external IP address. So let me click Create. I can leave the name. You have obviously a selection of regions and zones you can choose, but I want to focus on the IP addresses. So let me go down to this option, Expand Management Security Bits Networking Sole Tenancy. Let's focus on networking. And here I have the network interface. I'm going to click the pencil icon. I can choose between the different networks. So if I had different networks, I could choose between them. That's not the case here. And then I have the primary internal IP and external IP. So if we look at those options, you can see that I can choose an ephemeral address, either the one that's created automatically, or I could custom select one. So within the range that I have here, I could just type an IP address. I could also reserve a static internal IP address. This is great if you want to keep that IP address for a longer time. And we have similar options with the external IP address, but one of the big differences is that you can also just select none. So as I mentioned, your instances don't need to have an external IP address. So let's just leave this as ephemeral. And by the way, with the /20 here, we have a lot of space in this IP range, over 4,000 addresses. So we could definitely have that many instances. There are also limits of how many instances you can have per network. As of this recording, it's actually 15,000. So do keep that in mind. You might have a very large IP range, but that doesn't mean that you actually can create that many instances. And that's a quota. There may also be actual limitations on physical hardware that's even available within a specific region or zone. So let me go ahead and create this instance. And we're going to keep an eye on the internal and as well as the external IP address once the instance is created. And then we're also going to stop and start the instance to see if any of the IP addresses change. So here we can see the internal IP address. So that is definitely within that space that we just looked at. The external IP address obviously is within Google's range here, and we could have reserved that, but this is an ephemeral one. So let's actually test this out. I'm going to select the instance. I'm going to stop it. So it's telling me that if it doesn't complete within 90 seconds, it might be forced. So if you had any shutdown scripts in here, you want to make sure that they can actually complete within 90 seconds. So let's run through that. And remember this external IP address that we currently have here, as well as the internal IP address. So this is going to take its time now. We can also click refresh to keep an eye on this. But this will take about 90 seconds, and that's just to give your shutdown script enough time to perform any task to gracefully shut down this instance. So here we are. We can see the instance is stopped. The external IP address is gone. So now we're just going to start up that instance again. It's going to tell us that we're going to be billed while it's running. That's fine. And you can see that the internal IP address remained the same while this instance stopped. So that has actually stayed for the time being. And now while this instance spins up, which we can, by the way, monitor the progress over here, we should see that we should be getting a new.
Regardless of whether you use an ephemeral or static IP address, the external address is unknown to the OS of the VM. The external IP address is mapped to the VM's internal address transparently by VPC. I am illustrating this here by running ifconfig within a VM in Google Cloud, which only returns the internal IP address. Let's explore this further by looking at DNS resolution for both internal and external addresses. Let's start with internal addresses. Google Cloud has two types of internal DNS names, zonal and global, project-wide DNS. In general, Google strongly recommends using zonal DNS because it offers higher reliability guarantees by isolating failures in the DNS registration to individual zones. Each instance has a hostname that can be resolved to an internal IP address. This hostname is the same as the instance name. There is also an internal fully qualified domain name, or FQDN, for an instance that uses the format shown on the slide. If you delete and recreate an instance, the internal IP address can change. This change can disrupt connections from other compute engine resources, which must obtain the new IP address before they can connect again. However, the DNS name always points to a specific instance, no matter what the internal IP address is. Each instance has a metadata server that also acts as a DNS resolver for that instance. The metadata server handles all DNS queries for local network resources and routes all other queries to Google's public DNS servers for public name resolution. I previously mentioned that an instance is not aware of any external IP address assigned to it. Instead, the network stores a lookup table that matches external IP addresses with the internal IP addresses of the relevant instances.
Now, let's look at external addresses. Instances with external IP addresses can allow connections from hosts outside of the project. Users can do so directly using the external IP address. Public DNS records pointing to instances are not published automatically. However, admins can publish these using existing DNS servers. Domain name servers can be hosted on GCP using Cloud DNS. This is a managed service that's definitely worth considering, so let's explore it in more detail. Cloud DNS is a scalable, reliable, and managed authoritative domain name system, or DNS service, running on the same infrastructure as Google. Cloud DNS translates requests for domain names like google.com into IP addresses. Cloud DNS uses Google's global network of anycast name servers to serve your DNS zones from redundant locations around the world, providing lower latency and high availability for your users. High availability is very important because if you can't look up a domain name, the internet might as well be down. That's why GCP offers a 100% uptime service level agreement, or SLA, for domains configured in Cloud DNS. Cloud DNS lets you create and update millions of DNS records without the burden of managing your own DNS servers and software. Instead, you use a simple user interface, command line interface, or API. Another networking feature of GCP is alias IP ranges. Alias IP ranges let you assign a range of internal addresses as an alias to a virtual machine's network interface. This is useful if you have multiple services.
Alias IP range releases a range of internal addresses and areas to virtual machines.
Running on a VM, and you want to assign a different IP address to each service. In essence, you can configure multiple IP addresses representing containers or applications hosted in a VM without having to define a separate network interface. You just draw the alias IP range from the local subnet's primary or secondary CIDR ranges. This diagram provides a basic illustration of primary and secondary CIDR ranges and VM alias IP ranges.
Okay. Need to rewatch something.
Alias IP ranges let you assign a range of internal addresses as an alias to a virtual machine's network interface. This is useful if you have multiple services running on a VM and you want to assign a different IP address to each service. In essence, you can configure multiple IP addresses representing containers or applications hosted in a VM without having to define a separate network interface. You just draw the alias IP range from the local subnet's primary or secondary CIDR ranges. This diagram provides a basic illustration of primary and secondary CIDR ranges and VM alias IP ranges.
Okay. Nice. So now we arrived at a good part of this module. We're still not at the lab. We're already filming since 1 hour. Okay. We knew it was a long module. So IP addresses for default domains. Google publishes the complete list of IP ranges that it announces to the internet in GloofJSON. Google also publishes a list of Google Cloud customer usable global and regional external IP addresses ranging in CloudJSON. The following files replace the SPF Google record recommended to use for listing Google IP addresses. So gstatic, interesting resources, IP ranges, okay, so I will save this in this course folder and let's go.
So far, you've learned about projects, networks, subnetworks, and IP addresses. Let's use what you learned to understand how GCP routes traffic. By default, every network has routes that let instances in a network send traffic directly to each other, even across subnets. In addition, every network has a default route that directs packets to destinations that are outside the network. Although these routes cover most of your normal routing needs, you can also create special routes that override these routes. Just creating a route does not ensure that your packets will be received by the specified next hop. Firewall rules must also allow the packet. The default network has pre-configured firewall rules that allow all instances in the network to talk with each other. Manually created networks do not have such rules, so you must create them, as you will experience in the first lab. Routes match packets by destination IP addresses. However, no traffic will flow without.
Okay, so all type of networks generated from inside and outside has to be routed to a destination. Apply to traffic egressing a VM. Forward traffic to most specific route are created when subnet is created. Enable VMs on same network to communicate. Destination is CIDR notation. Traffic is delivered only if it's also mentions firewall rule.
Also matching a firewall rule. A route is created when a network is created, enabling traffic delivery from anywhere. Also, a route is created when a subnet is created. This is what enables VMs on the same network to communicate. This slide shows a simplified routing table, but let's look at this in more detail. Each route in the routes collection may apply to one or more instances. A route applies to an instance if the network and instance tags match. If the network matches and there are no instance tags specified, the route applies to all instances in that network. Compute Engine then uses the routes collection to create. This slide shows a simplified routing table. Route is created when a subnet is created. This is what enables VMs on the same network.
Hey, stop. Okay, so let's go slower. VM routing table. So destination, this one. Okay, so it goes there. Destination, this one. So it goes there because it's part of these IP ranges. And then 000, it goes to the internet. Wow. And this one will go here. Okay.
Network to communicate. This slide shows a simplified routing table, but let's look at this in more detail. Each route in the routes collection may apply to one or more instances. A route applies to an instance if the network and instance tags match. If the network matches and there are no instance tags specified, the route applies to all instances in that network. Compute Engine then uses the routes collection to create individual read-only routing tables for each instance. This diagram shows a massively scalable virtual router at the core of each network. Every virtual machine instance in the network is directly connected to this router, and all packets leaving a virtual machine instance are first handled at this layer before they are forwarded to the next hop. The virtual network router selects the next hop for a packet by consulting the routing table for that instance. GCP firewall rules protect your virtual machine instances from unapproved connections, both inbound and outbound, known as ingress and egress respectively. Essentially, every VPC network functions as a distributed firewall. Although firewall rules are applied to the network as a whole, connections are allowed or denied at the instance level. You can think of the firewall as existing not only between your instances and other networks, but between individual instances within the same network. GCP firewall rules are stateful. This means that if a connection is allowed between a source and a target, or a target and a destination, all subsequent traffic in either direction will be allowed. In other words, firewall rules allow bidirectional communication once a session is established. Also, if for some reason all firewall rules in a network are deleted, there is still an implied deny all ingress rule and an implied allow all egress rule for the network. You can express your desired firewall configuration as a set of firewall rules. Conceptually, a firewall rule is composed of the following parameters: the direction of the rule. Inbound connections are matched against ingress rules only, and outbound connections are matched against egress rules only. The source of the connection for ingress packets, or the destination of the connection for egress packets. The protocol and port of the connection, where any rule can be restricted to apply to specific protocols only, or specific combinations of protocols and ports only. The action of the rule, which is to allow or deny packets that match the direction, protocol, port, and source or destination of the rule. The priority of the rule, which governs the order in which rules are evaluated. The first matching rule is applied. The rule assignment. By default, all rules are assigned to all instances, but you can assign certain rules to certain instances only. For more information on firewall rule components, please refer to the link section of this video. Let's look at some GCP firewall rule use cases for both egress and ingress. Egress firewall rules control outgoing connections originated inside your GCP network. Egress allow rules allow outbound connections that match specific protocol ports and IP addresses. Egress deny rules prevent instances from initiating connections that match non-permitted port, protocol, and IP range combinations. For egress firewall rules, destinations to which a rule applies may be specified using IP CIDR ranges. Specifically, you can use the destination ranges to protect from undesired connections initiated by a VM instance towards an external host, as shown on the left. You can also use destination ranges to prevent undesired connections from internal VM instances to specific GCP CIDR ranges. This is illustrated in the middle, where a VM in a specific subnet is shown attempting to connect inappropriately to another VM within the same network. Ingress firewall rules protect against incoming connections to the instance from any source. Ingress allow rules allow specific protocol ports and IP ranges to connect in. The firewall prevents instances from receiving connections on non-permitted ports and protocols. Rules can be restricted to only affect particular sources. Source CIDR ranges can be used to protect an instance from undesired connections coming either from external networks or from GCP IP ranges. This diagram illustrates a VM receiving a connection from an external address and another VM receiving a connection from a VM within the same network. You can control ingress connections from a VM instance by constructing inbound connection conditions using source CIDR ranges, protocols, or ports. Before you apply what you just learned, let's talk about network pricing. It is important that you understand the circumstances in which you are built for GCP's network. This table is from the Compute Engine documentation, and it lists the price of each traffic type. First of all, ingress or traffic coming into GCP's network is not charged unless there is a resource, such as a load balancer, that is processing ingress traffic. Responses to requests count as egress and are charged. The rest of this table lists egress or traffic leaving a virtual machine. Egress traffic to the same zone is not charged as long as that egress is through the internal IP address of an instance. Also, egress traffic to Google products like YouTube, Maps, Drive, or traffic to a different GCP service within the same region is not charged for. However, there is a charge for egress between zones in the same region, egress within a zone if the traffic is through the external IP address of an instance, and egress between regions. As for the difference in egress traffic to the same zone, Compute Engine cannot
determine the zone of a virtual machine through the external IP address. Therefore, this traffic is treated like egress between zones in the same region. Also, there are some exceptions, and pricing can always change, so refer to the documentation in the link section of these slides. Now, you are charged for static and ephemeral external IP addresses. This table represents the external IP pricing for US Central 1 as of this recording. You can see that if you reserve a static external IP address and do not assign it to a resource, such as a VM instance or a forwarding rule, you are charged at a higher rate than for static and ephemeral external IP addresses that are in use. Also, external IP addresses on preemptible VMs have a lower charge than for standard VM instances. Remember, pricing can always change, so please refer to the documentation link in the slides. Also, I recommend using the GCP pricing calculator to estimate the cost of a collection of resources, because each GCP service has its own pricing model. The pricing calculator is a web-based tool that you use to specify the expected consumption of certain services and resources, and it then provides you with an estimated cost. For example, you can specify a specific instance type in a specific region, along with 100 gigabytes of monthly egress traffic to Americas and EMEA. The pricing calculator then returns the total estimated cost. You can adjust the currency and time frame to meet your needs, and when you finish, you can email the estimate or save it to a specific URL for future reference. To use the pricing calculator today, refer to the link in the slide.
Let's apply some of the network features we just discussed in a lab. In this lab, you create an auto mode VPC network with firewall rules and 2 VM instances. Then you convert the auto mode network to a custom mode network and create other custom mode networks. Let's apply some of the network features we just discussed in a lab. In this lab, you create an auto mode VPC network with firewall rules and 2 VM instances. Then you convert the auto mode network to a custom mode network and create other custom mode networks as shown in this network diagram. You also explore the connectivity across networks.
Great, so let's practice. 1 hour and 30. So imagine that will not be the fastest in the world, because usually this is a quite accurate estimation. I will just, I assume that I will take at least 1 hour. So start. Now we already registered for 1 hour. Therefore, I will try to go as fast as possible. Okay, so I have the console here. Task 1, explore the default network. So default network has a subnet in each region. Navigation menu, VPC networks, default with its subnets. Each subnet is associated with a Google Cloud region, a private CIDR, block of fixed internal IP address range, and gateway. So let's go there, even if we already had this type of exercise. So here we have all the subnets with the region, the gateway. What else? Yeah, that's all. Yeah, there's this range. Okay. View the routes. Default internet gateway routes. The routes are managed for you. You can create custom static routes. Okay, so routes are here for default. And the region is US West 1A. View. So we have all the routes here. So for each destination range, mosquito. Okay. View the firewall rules. Oh, yeah. So we have the default rules, the 4 default rules, plus the 2 implied rules, which are not shown here. Delete the firewall rules. So it's beginning the nasty stuff here. Delete. Okay. Delete the default network. Fuck. So default network, VPC networks, delete default, deleting default network. Wait for the network to be deleted. There are no routes, there are no firewall rules. Without a VPC network, you cannot create VM instances, containers, or append an application through. Try to create a VM instance. I will receive just an error. Okay, so task 2, create an automod network. Create VPC network, name it my network, firewall rules, subnet creation mode, automatic. Come on. I have to wait. Let's see if it already did it. Sometimes it works. No. So let's see if we can just create a VPC network while, okay. So name will be my network, and then subnet creation mode, automatic. For firewall rules, select all available rules. And then these are the same standard for rules at the default. The displayed rules have lower priority. Click create. Okay. When the network is ready, click my network subnet, not IP address range for the subnets US West 1 and Asia East 1. If you ever delete the default network, you can quickly recreate it by creating an automod network as you just did. So create a VM instance in US West 1. I think that you will still need to wait. So name will be mynet US VM. Okay, let's just wait for the confirmation. Created. So create an instance. Let's go. The instance will be called like this. Region West 1A. Machine type E2 micro. Boot disk Debian GNU Linux 12. Perfect. Create. And then we'll do the same for Asia East 1 with the name not US. Create another instance. Okay. Which was Asia East 1. A, right? Same type of machine, same type of image. And then create. Okay. Note, the external IP addresses for both are ephemeral. Pull and become available when stopped instance. Okay, verify connectivity for the VM instances. So the firewall rules that you created with my network allow ingress SSH. Okay. So I will go to the not US virtual machine, start SSH, and launch this. Okay, so I need for both of them to take note of the IP address. So notes. Okay, first machine has internal like this, and come on, internal. So it's saying to go in the not US. Sorry. Form. Okay, so it's saying the contrary. Okay. Where is? So this is the Node.js virtual machine. And it's saying for my Node.js, click SSH and start. Okay. So from the US, we share with you the screen capture. Yeah. Therefore, authorize. Okay. Establishing connection to SSH server. Now, from here, we will just do a ping and the IP address will be the internal Node.js. Okay, so it will be this one. The ping works. This because we have, it says allow custom firewall, but I think it's because I have ICMP, not sure. So then we'll test the same, but through IP public address. So let's delete the internal. Through IP public address, we can communicate because of ICMP, right? ICMP. You can SSH to my network internal because we have SSH allowed. Okay. Convert the network to a custom mode network. So this is something I didn't do. Okay, this is the other task, subtask in task 2. So in VPC networks, click my network, edit, custom, select custom from subnet creation mode. So in networks, my network, edit. Okay, save, right? Click save, return to the VPC networks page. Okay, so wait for more networks to change to custom. You can click refresh while you wait. Check my progress. Let's see if it's true. Okay, so let's check again. Ah, come on. Okay, now it should be. Yeah. Task 3. Create a custom mode network. Create custom mode networks. You have been tasked to create 2 additional custom networks. Management net and private net, along with firewall rules to allow SSH, ICMP, and RDP ingress traffic and VM instance as shown in the example diagram. So we need to create these other 2. Okay, so these are the 2 networks. We already have this one for okay. Note that the API CI CIDR ranges of this network do not overlap. This allows you to set up mechanisms such as VPC peering between the networks. So this will be 2 separate VPC networks, and each will have its subnetwork. Okay. So we'll do the network management first. We'll go to VPC, create VPC. We'll assign this name, custom type. And okay, specify the following and leave the remaining set yes that false. Okay, so the VPC will be called like this. Create VPC network called like this. Subnet type custom. So for the first subnet and only for this VPC, we'll assign this name, US West 1. And then the IPv4 range will be class A submask 20. Done. Click equivalent command line. These commands illustrate that networks can be created using the gcloud command line. You will create a private network using commands with similar parameters. It's in the end, but equivalent command line. Copy. I will copy all of these in my in the text editor. What the fuck? Okay. Just to see if I copied both of them or just one of them. Looks like I copied just one of them. I copied both and it was just okay. Okay, so close, then create. Create the private network. So now we'll do the same for the private network, but from the Cloud Shell. Okay. So I prompted click continue to create a private network, run the following command, click authorize if prompted. G-Cloud Compute Networks, create private net, custom. Successfully created network management net, okay. Now we have the Cloud Shell active and we'll do a VPC creation from here. So G-Cloud Compute Networks, create private net, subnet mode custom, authorize, and then we'll create the private subnet US. Okay, with this region and this IP range. Okay. Great. And then the other subnet. So now we get a list of the networks. Okay, G Cloud Compute Network. We have management net, my network, and private net. all custom, all IPv4. Okay. So subnet list, sort by network. So we have a lot of subnets because in the first one we have a lot of auto created subnets. Verify that the same networks and subnet are listed in the Google Cloud Console. Yeah, I trust them. So create the firewall rules for management net. Okay, we go to firewall. Create firewall rule. Oh shit. So specify the following and leave the remaining settings as the defaults. This will be a firewall rule for management, network management net. Targets all instances in the network. IPv4 ranges 000. Then specified protocols and ports. Follows ingress traffic to VM instance. Okay, SSH, SMP, and RDP. Specify protocol and ports. What the fuck? ICMP, SSH, and RDP. Now to make sure to include 0 and 0. Okay, select TCP and specify. TCP and specify 22 and 3389. Okay, so check equivalent command line. Just before I copy it, even if I think it's just to have an idea. What the fuck? You will create a price or rules using this commands with similar parameters. Create. Man, what the fuck? Other protocol. I mean, like ACMP instead of ICMP all upcase. Okay. Now we'll do the same. Return if necessary to create a rule on the following command. Okay. This should be faster as we already started today the Cloud Shell. So this command, which is similar to this one, we are creating the private network firewall policies. Okay, so we have an output like this to list all the firewall rules. Now we can use this command. And then, okay, we have the firewall rules for my network have been created for you. You can define multiple protocols and firewalls or span across multiple rules. Verified info, check my progress. We have it. Next, create 2 VM instances. Okay, it's a tedious work, but we have to do it. Okay, so let's go to the cloud compute engine, create an instance called like this, US1, okay. And WLX, create. Last, oh, Jesus fucking Christ. I just clicked create without reasoning. Delete, delete. So create an instance called, come on. Something happened here with the user interface. Okay, so we have this name, this region. Come on, now will not be in use anymore. Well, it may take a lot for a VM to be deleted. Okay, what can we do? We'll create a private US VM with this command. God, it's taking forever. What the fuck? So I crashed GCP for a couple of minutes. And we're back again with this new try. It will be a West one, right? E2 micro. And then advanced options, networking. For network interfaces, click the drop-down arrow and select these two. Okay. Hello, Domingo. Okay. Sorry, so I got distracted. For network interfaces, click the drop-down arrow to edit. Network management net. Management net, subnet US. It's already done. So click done and then create. Fuck. So in the end, it was all right to leave it like this. Well, perfect. We already did this one. Let's see. Okay, so the virtual machine was created. Perfect. You can explore more network information by clicking to me. Okay. So explore the connectivity across networks. Therefore, we go to the VM instances. We take note of the external IP address for the not US VM in my net. Okay. Hello. Hello. Would you like to come here with me? Up, up. Crying because she wants to practice subnetting too. Say hi. Hello. Okay. So now we already have noted down the not US VM data. So let's go in VM instances, management net US VM. Okay. And we take note of the internal and external IP. Okay. And then for private net US VM, private net US VM, we take note also for this virtual machine of its addresses. Okay. Now we're ready to start pinging. So to test the connectivity from my net, not US VM external IP, run the following command. My net US VM. Okay. My net US VM SSH. Authorize. So you can see this. Yeah. Oh, I'm out of focus. Who cares? Let's go. So from this virtual machine, we'll contact my net, not US external IP. Okay. So the command is this one. Let's go. So this is machine in the US, contacting my not US external IP. So, okay, it's working. We'll do the same with the management US VM external IP. So it's this other IP. And this should work too. Okay. And another external IP, which is the private net. So this one should work too. So basically, in all the cases, the external IP ping is working because of ICMP allowed all the ingress firewall rules are allowed for all the instances for ICMP. Ping the internal IP addresses. Ping the internal IP addresses of the VM instances to determine whether you can reach the instances from within a VPC network. Which instances should you be able to ping from mynet US VM using internal IP addresses? Mynet, not US. That's all. So compute engine VM instances, not the internal IP addresses, okay, run 23 SSH mynet US VM. Okay, okay, review. So in this lab, you explored the default network and determined that you cannot create VM instances without a VPC network. Thus, you created a new auto mode VPC network with subnets, routes, firewall rules, and 2 VM instances, and tested the connectivity for the VM instances. Because auto mode networks aren't recommended for production, you converted the auto mode network to a custom mode network, Domingo. So remember, next you created 2 more custom mode VPC networks with firewall rules and VM instances using Cloud Console and G-Cloud command line. Then you tested the connectivity across VPC networks, which worked when pinging external IP addresses, but not when pinging internal IP addresses. VPC networks are by default isolated private networking domains. Therefore, no internal IP addresses communication is allowed between networks, unless you set up mechanisms such VPC peering or VPN, Domingo. So I imagine this will be the next topic. The next lab will be a kind of exercise about VPC peering and VPN. For now, I will conclude here.
In this lab, you explored the
This is
default
just a
network
lab
and determined that you
review.
cannot create VM.
With someone reproducing the same exercise, not go through it again.
And we can see that that's not. Let's use what we have learned so far and look at common network designs.
Okay, this is already the next topic. Therefore, I will conclude here. I salute you and